So our next speaker is Daniel Hansson from Verifighter. He's going to speak on automatic validated debut of the, I think that means debug, of regression failures. It says debut.
Debug.
There's a bug in the debug. So automatic validated debug of regression failures. Daniel is CEO of Verifighter and has more than 15 years experience as an ASIC designer and project manager from Ericsson, Texas Instruments and Arc Cores. The last 6 years he has spent on Pindown, the automatic debug tool for regression testing. And he's speaking from Sweden today. Over to you, Daniel. Thank you.
Thanks, Mike. So yes, I'm going to talk about automatic debug and especially our automatic debug tool, Pindown, which Mike mentioned. But I was thinking of starting a bit more generic, laying down the rules for automatic debug if anyone in the audience wants to do their own automatic debug tool. Okay, so as you know, I think Mike also said some percentage figure. This is another percentage figure. There's a lot of debug going on. I'll just skip through this slide very quickly. This one comes from Harris Foster at Mentor Graphics, where he says the biggest verification task is a debug, 37%. Let's go to the next one. And the reason why we are here now and not earlier is because what has happened over the last 15, 20 years is that designs have become larger. Random testing means that there's a much larger quantity of tests being run, and automated testing, where you kick off tests regularly, means there's a whole lot more tests being run much more often, and that's why debug is now a big topic, and I think it's going to be the next thing that needs to be automated. Okay, so let's look at the manual debug first. So it's basically consists of 3 steps. Step number 1 is you have to analyze the problem. Some super smart verification engineer has to look into the problem and see what it is. Then you need to modify the code and validate it. Whatever test that failed, you need to run it again to make sure that that the test is now passing. Even if in this case, this verification engineer is Einstein, so he's very smart, but he may have identified something that is correct, but it's not the full picture. There may be 2 bugs or 3 bugs, or he may actually be wrong. And there may be thousands of reasons. So you always have to validate your guess or your intelligent guess. And in the end, also, you want it to pass because that's the whole purpose. You want to fix the bug. Okay, so if you compare that to automatic debug, and this is generic, this slide. It has nothing to do with Pindown yet. This is just a generic slide on anything you want to automate when it comes to automatic debug. You still have the same steps. You need to analyze, modify, and validate. But the one thing which is different is you can't have the computers cannot be so as smart as Einstein or a verification engineer. So you need a limited search space. Whatever you define that your automatic debug tool should automatically debug, it has to has a limit to it. It has to have the ends, because it cannot go off like a human on a track and find any type of errors. And the second thing is that the debug analysis must be validated. That's not different from manual debug. That's exactly the same step as before. And I would say also it's something which is true for anything you want to automate also. You must be certain that when you automate something that it is 100% robust. You can't automate stuff which is sometimes wrong, sometimes right. It has to be a robust solution for people to rely on it and not try to second guess what it's doing. So the summary of this is the laws of automatic debug. You have to have a limited search space, and you must validate the debug analysis. Okay, so now I'm going to go into and talk about our solution. So pin down is an automatic debugger of regression failures. So our limited search space is basically that it's a regression bug, it's a regression failure. This is something that has passed before, but it's not passing any longer. So something has happened. Some combinations of commits has happened that has caused it to fail. So it's a limited search space. And pin down modifies the code and try to make it run again. So that also fulfills the second law of the automatic debug, which is to validate its debug analysis. But let's go through it step by step. So step one is you basically have one test that fails, and 9 in this case means that's the latest. That's where you run the test on. So that's the revision if you think is subversion, or the change list if you think perforce. But it's basically the latest stuff. And at that point, you only know that there's something that failed. You don't know the status of anything back in history. The next step, step 2, is that pin down reruns the same test failure on older revisions in order to find out the status. And when it does that, it sees that this test has passed back in history. So it has here identified a limited search space. If this test would have failed all the way back, no matter how far back you go in history, pin down would not have a limited search space, and it would come back and basically say this test has always failed. It could be, for example, if you have a run of test with a new scenario, that new scenario may discover a new case you have never tested before, rather than a recent mistake. Okay, but in this case, it was we have a limited search space. Step 3 is that pin down will now try to make the test pass again by modifying the code. So in this example, it will remove whatever was done in commit 6 here, and rerun the test on the latest, on revision 9 here. So everything looks exactly as when you ran the test the first time and it failed, except that whatever was changed in 6 is gone. 7, 8, 9 is still there. But in this case, it still fails. So that was obviously not the reason. Even though it started to fail on 6, that issue was probably fixed maybe in 8. So that is no longer the reason the test is still failing. So pin down will continue looking, and it will then try to remove 7 instead. And when it removes 7, it achieves a pass, and thereby it has been validated. So that's the core principle of how this works. Okay, so if you do debugging with pin down, instead of leaving it to a SAD engineer in this case, who will have to do a manual approach, and it's iterative because he has to discuss it, and he doesn't know if his analysis is right or wrong because there's no validation until you've actually fixed the bug. With pin down instead, you can automate this process. So you automate it, you send a bug report is sent directly to that person, and most importantly, it's validated. The test has been made to pass locally before it's sent to this person. And I should say also that pin down doesn't check in the changes. It only modifies the code locally to prove the point, then sends the bug to this person and says, okay, I succeeded, and you're the evil guy. It looks something like this, a bug report, where basically the log file here comes from basically your system, your log files, where pin down extracts a failure message, and it's associated with a commit. And for small commits, you see the actual changes straight in the email. The commit in this case was this one, 5958, bug number 2. And the reason it has that message is because I used this in an online demo video where I insert bugs and show that pin down can find them. That one is available on our website. But the most important one is here, this sentence here. So it says, validated true, pin down made the failing test pass again by only removing the bad commit. This was done locally, nothing was committed. So this is the confidence building sentence that makes this guy down here. Not to debate it, but rather just fix it. Pinna looks like this. It's basically an internal web server that talks directly to the version control system, its own result database, and to your LSF or SGE-driven farm, and it can send out email bug reports. So the structure of the software is similar to Jenkins, if you're familiar with that. It's just the precision that is different. And when you run it, it will look something like this. You have a script which launches hundreds of tests on the farm, and in this case there are 10 failures. And then Pindown will use 10 slots on the farm during its debug. When it goes back in time, it uses 10. It tests 10 different versions of the code in parallel. So it's a much lower load than your initial script. And they will send out bug reports after it has concluded the debug for each of them. Okay, so this is how it looks like, the algorithm in a bit more detail. I'm just going to check out time. Okay, it seems I have plenty of time. Okay, so this is one of the heavier slides, so I will spend some time here. But the way Pinna works is that it first groups the error messages according to their failure messages. So in this case, you have 12 test failures with this error message, and you have 14 test failure with this error message. And then Pinna picks just the fastest test in bug group 1. And then it selects, it first goes back in time, so it selects 10 older versions of the code to test, to rerun the same test and the same seed. And these 10 is illustrated by this little figure here. And this is a binary search. It's a parallel binary search. So these, when you go back in time, if you say you have 1,000 commits that have occurred recently, Pinna will test every 100 commit to see the test results, and then it will go around. It will iterate around here. So in the next iteration, it will zoom in on the 100 chunk where it saw a transition from pass to fail, and test every 10 commits and then every 1 commit. So in just 3 iterations, the time it takes to rerun one test 3 times, it will have zoomed in on the potential bad commit if you have 1,000 commits. So it will basically just test 30 snapshots out of 1,000 possible snapshots. So it's very fast. It has very fast search algorithm. But in the end, it will modify, and it's of course much faster if you just have like 100 commits per day or something like that. Then you save. You can zoom in on the 100 chunk immediately. Okay, but the end of this loop is that the test passes. Pinna modifies the code by removing a bad commit. It makes the test pass, and then this bug report is sent out here to this guy here with this change list, and this is a little version of the bug report I showed before. So all we've done so far is take the fastest test from bug group 1 and make it pass again. We made the failing test pass again, and we send out a bug report to the person who was responsible for making it fail in the first place. Okay, so what do we do with the rest of the test? Because I've consumed almost all my slide here, but I've just debugged 1 test. And the answer is that we don't need to debug more tests in this group. Instead, you just go to step number 4, and you rerun the rest of the tests in the same group with this change list or revision unrolled. Because if the grouping was correct, and if all these tests fail for the same reason, and we manage to make the fastest test pass by unrolling this change list or revision, then if we undo that change list and just run the rest of the tests once, they should also all pass. So we don't need to do debug for the rest of the test, just the validation phase, which is just running the test once. Now, if let's say half of the test fail and half the test passes, then we go back here, we regroup with this new information. So in that case, the tests which didn't pass, they are now put into bug group number 2. The bug group number 1 has finished. And then we pick the fastest test in bug group number 2 and redo this exercise. So you can handle vast amounts of test failures because it only does the debug on the fastest test in each group, and then it just validates the rest of the test. It just tries to make this, it just runs them once to make them pass again in the same way in the fastest test passing. And also the binary search algorithm makes it not so sensitive for number of commits. Okay, so if I go to the next slide. Okay, so so far I've just shown you the simple solution, the simple approach, which is illustrated by this line here. You have something failed here, and you see it as just one line of commits. But in reality, there are many cases which are much more complicated and very common. So, for example, overlapping failures 1. That's the scenario where it's still just one test that fails, but there are 2 issues checked in, and each issue is illustrated by its own line. So, and this is actually it looks very similar to the first example I showed of Pindown. Here, Pindown will first take 6 because that's the first time it failed. It will try to make it pass again on 9. It doesn't work, so it comes back and does it on try to remove 7. And when it removes 7, it makes it pass again on 9. So it can only be validated by unrolling, removing commit numbers 7 here. So that was the first example. But a variant of that is that you can have both issues still open. And these issues can be unrelated to just 2 bugs that happens to be inserted at the same time. Because the simple approach up here assumes that there's only ever one bug inserted in the system at any point, which is not true. So it's very common to have 2 bugs which affect the same commit. But it could also just be one bad commit plus a dependency. Two commits can be so tightly dependent that they cannot be separated. And in that case, Pindown will say that, okay, I can only make this test pass again if I unroll both 6 and 7. So it still validates it, but it doesn't come back always with just 1. Sometimes it comes back with 2 commits in order to make it pass. And it could even be 3 or more. Random instability is another issue. It's not really illustrated well in this example here, but basically the further back in time you go with the older versions of the test bench, the higher risk for random instability, which means that the same seed number no longer produces a relevant test scenario. But Pindown minimizes random instability by the fact that it always goes back to the top. It uses the latest version of the test bench, exactly the same where the test started to fail, and then it just tries to remove 1 commit to make it pass. So the only chance to experience a random instability issue is that if that exists inside this commit that was unrolled. Okay, I see Mike's message here that I should hurry, so we can leave some time for questions, and I will obey Mike. So let me. So what we've seen is that the bug fixing is sped up 4 times if you have automatic debug, because you know what the problem is and you just fix it. that has reduced the project time by 11% in one project we measured and 10% in another. Basically, the faster bug churning, the better for the project time, especially in the later phase of the project. And to sum it up, so the laws of automatic debug, in case you want to do your own automatic debug tool, is you have to identify a limited search space, which in this case was regression failures. Regression failures, which means something has passed before, or it could be you follow the logic cone back or whatever, but it has to be a limited search space. And the debug analysis must be validated. It can't be a good guess. And with Pinna, we have that for regression failures, and it's all very good. And I'm sure there are questions now.
Thank you, Daniel. Yeah, you're right. We do have some time for questions. And we have one question online, which we'll go to first. Is this Subversion based? Any other revision control tools supported? So that's a question from online, Daniel.
We support Perforce, Git, Mercurial, ClearCase, and I think that was it. Perforce, Git, Mercurial, the Subversion, and the ClearCase.
Okay, thank you. I'm going to see if there's any questions in Bristol. So there's no questions from Bristol. So just remains to say thank you very much, Daniel, and I'll see you at DAC as well. You'll be at DAC, Daniel? Maybe not.
Yeah, see you there, Mike.
Okay, thank you. Bye.
Cheers, bye.